record that. All right, and get this up here. I thought this morning we were going to be working on type 2A, and then I thought, well, I said, no, let's go and get this land air problem out of the way. And then first hour, I'm not saying they didn't show up. They may have shown up early because they didn't realize it's flex day. So they showed up at 9. Well, I'm still in bed at 9. Class starts at 10 a.m. on Wednesdays. Anywho, so missed them. And then second hour, we ended up just working on this Planet X problem. So that's what we're going to do today is just Planet X. In the limited time, Wednesdays is the shortest class of the week. So here we go. Let's see what's going on. I'll put another one of these up. Tomorrow's back to regular schedule, which for you doesn't matter. It's 1:10 to 1:50 tomorrow. Is that right? 1:10 to 2 o'clock tomorrow. Today's 1:10 to 1:50, and maybe even shorter than that. Okay, we did all that. This will come in handy if you're doing that homework. The homework tonight, it's like I was telling the boys there before we came on air, the homework tonight is a blue. It's the blue box here. In the X direction, you're going to use this equation. Hold on. You're going to use this for the homework tonight. You're going to use this equation in the X, and then you're going to use this stuff to do the vertical stuff. But we'll talk about that more in a minute. Okay, it's all old stuff. All right, now, so I did this. This is important. So I did this. We talked about this in here a little bit yesterday, and then I dressed it up a little bit before I put it onto the screenshots. But this is going to come in. This is part of what's going on here. So in this problem, the Planet X problem, we're looking at type 1 projectile motion. That's this. I've animated this where I put colors on this, but that's those red balls hanging from strings. And so on Earth, it's going to come down a lot faster, but on Planet X, it takes 2.75 seconds for the ball to fall the 94 centimeters and move over the 165 centimeters. Okay, so we've got to plot this up properly today. Also wanted to show you this. I like this screenshot I found from years past. And this is a type 1 projectile motion, but it makes the point. What I like about this is the color coding. So when the ball first comes off the table, it looks like it's black there. And then let's say 1 second later, just to keep it simple, it's the red ball. Okay, it's the same ball. It's just showing where it is vertically and horizontally. Actually, it's where it is on the this here is the combination, right, of vertical and horizontal. But it shows where it is. I don't like that one. Let me change that. There we go. So it shows where it is vertically here and then horizontally. So in the first second, it's right there. In the second second, it's like this thing is in free fall, is all it is. The ball's in free fall. It just happens to be on a conveyor belt, and the conveyor belt is this Newton's first law, right? The object in motion stays in motion. So that's the idea of a conveyor belt there. So it keeps going. This is assuming the air drag is minimal. Newton's first law. We'll finally get to second and third here later on. But the purple is the next second. The blue shows where the ball is. If it were the projection of the ball onto the wall here, where the ball actually is, would be here, and the projection's right here. And then the green is where it's falling. But you can look at that and say, okay, that is basically the second blue equation shows the verticalness, the second blue. And then this is a combination of the combination of red and second blue. Okay. So what I want to do is on this graph that we started a couple times ago, I noticed what I was doing was from a key, and that key turned out to be wrong a little bit, slightly off. So I just redid it, and that's these values here. So first thing I want you to do is get out the graph on the front of 5.1. We're going to wrap that up today It's, you know, it's a flex day. I don't want to do anything brand new like the land air problem. We'll do that tomorrow. Don't miss tomorrow, because that's a top 10 problem of the year. Or watch the recording, either one. So let's go through and plot these dots. Hopefully you can read that. Pull this up a little bit. We're going to plot the dots. Okay. Yeah, so this is going to be exciting. Tell you what, I'm going to pause it because, no, we'll keep going. Here we go. If they're watching from India, they can play at home. So 0, 0. I suppose when I take this on the road, this class, and make it for real, then I'll have to have a book. I'll have to have a 200-page book that gets sent to the person, or a PDF. So like it's an iPad. Maybe I require iPads. It's going to be too hard to deal with paper. What are they going to do? Send it to me through the mail, snail mail? Bring it to my front porch. Mr. Askey, I live in Kentucky. All right, so the next one is -2. So at 30, when we're over 30 centimeters, we're dropped -3, so practically nothing. It's, you know, it's type 1, comes off horizontally. 45 centimeters is drop 5. 60 centimeters, 10. 75 is 16. 90 is -25. 105 is -35. 120 is -50. Now see, we're picking up steam in the y direction. We're not picking up any steam in the x direction, thus the parabola. 135, 62. 62, 150 is 79 down, about 80 then. And finally, 165 or 94 down. That's what these are actual measurements students did on the hangy balls. Okay, so now take these and let's go ahead and connect them up. Don't connect them, but give me a smooth curve. We don't need that table anymore. Probably do this in pencil, right? Nature paints with a broad brush so you can make it nice and thick. We're not necessarily hitting every dot. There is some error in here. But it needs to come off with a flat. It needs to be flat right there at the beginning, because this is type 1. Okay, let me thicken that up. So this is the path of that toy gun ball coming out of that toy gun on planet X. And our task here is to find all this information about that planet. Okay, there's our data. We plotted our data. Now we got to come up with information. Well, that's what we're doing down here. And we did some of this stuff a while back, kind of the low-hanging fruit. Talk about low-hanging fruit. V naught y is simply 0. We got that one. Delta y, I can get that. That's -94 centimeters. Remember, we're dealing with the CGS system here. So we got to find V final y. Well, to find V final y, I need to find my gravity. So I got to find G, and that's one of the things we're supposed to find here. It says, what's the G on this planet? So now looking at this data and knowing that it's a total, the tau, knowing that tau is 2.75, how am I going to find G? Suggestions.
The first green.
Well, this wouldn't be a green situation because it's not launching. It's falling. So it's more like a blue situation. But which blue equation? All three of them have G in them. Which one of those three works for this situation? See, that's, you go, well, go ahead and tell us, Howski. Well, I'm not going to be here in about, what? March, April, May. In about 3 months, maybe stick around June, 4 months, I'll be gone. I'm out of the picture. No more waiting for Mr. Askey to come up with the equation. You're going to be on your own. And so that's the hardest part about physics, is coming up with the equation. I can plug numbers into an equation. I mean, come on. We can teach that to 5th graders. picking the equation that you need off. You go, I don't have my equation sheet. Well, then get them. You should have a PDF of all 10 equation sheets now, somewhere handy. Paper copies are nice because they're quick.
Would it not be the third?
The problem with the third is, because let's check the third. We're going to use the, well, okay, let's check the problem with third. Let's try the third. I mean, at least we're starting with somewhere, right? So V final y squared equals V naught y squared minus 2g delta y. I know delta y, check. I don't know g. I know V naught y, check, but I don't know V final. So I have two unknowns.
Okay.
That's right.
So the second blue?
Yeah, there we go. That's your process. You try the third, you go, oh, two unknowns. Okay, let's try another one. And that's what you do. A lot of physics is that. Just kind of go, what you try this one, let's try this one. All right, so the second one is delta y equals V naught y t minus 1/2 gt squared. Now we catch a break here, right? Because V naught is 0, V naught y is 0, not V naught, but V naught y. So now I can take this and I solve it for, I know my time too. That's 2.75, and I got to find g. So when I solve this for g, my new g, g would be minus 2 delta y over t squared. So I just isolated the variable. Now, if isolating variables still bothers you, you need to practice that. That just takes practice. It's rules. Okay, it's probably one of the most important things that comes out of Algebra 1. Anywho, so let's plug in then. Minus 2 times negative 94, see, because somebody earlier said, boy, you can't have, I thought you said g wasn't negative. No, it isn't, because delta y is negative. 94 centimeters divided by 2.75 seconds squared. Okay. So you punch, and what do we get? I think you get like 0.25. Let's say 0.25. Close enough. So G is, well, G is actually 25, but this with these units, you get 25. So G is 25 centimeters per second squared. And you go, whoa, I thought you said this was a small planet. Isn't that much bigger than the G on Earth? G on Earth is 9.81. What gives? Somebody want to talk me off the ledge here? What's going on? I had a big planet. I guess I made a mistake, eh?
It's in
9.81
centimeters.
Yeah.
Thank you. So this is centimeters per second squared. So the G of the Earth, of course, is 981 centimeters per second squared. So yes, indeed, this is a very small planet. In fact, calling it a planet, I think, is a joke, because the moon, over here now, the G of the moon, our moon, when I say moon, I mean our moon, is 167 centimeters per second squared. So this planet is more like an asteroid. And so that is a really small amount of gravity. If you were on this planet, if you run and take a leap, you're going to go jump over a creek. Probably wouldn't be a creek on this, but a rock. You're going to keep going up. You may, if you jump fast enough, you could achieve escape velocity and never come back. And that's a problem we have, because we're trying to land on comets. We're trying to land on asteroids. We're going to try and harvest an asteroid and bring it and orbit the Earth. Oh, by the way, speaking of space, tomorrow at 2:55, this is Thursday, at 2:55, I think it is, p.m., Perseverance, NASA's Perseverance is going to land on Mars. And it's kind of cool. All of a sudden, all these trips to Mars, right? Like 3 in a row, like China's going, and United Arab's going, America's going, because it was in that window when it was the cheapest and took the shortest amount of time to get there, because of Mars and Earth's orbits. So there's a window to launch. We launched a while back. It's finally at Mars, but it's going to land, and the landing is going to be outrageous. And I put on the Facebook group on the top, I put a link If you look at if you click on that opening picture, there's a link to about a 3-minute video. It's an animation. It's just like right out of science fiction. We're the aliens, man. Anyway, that's going to happen at 2:55 p.m. tomorrow. And one of the cool things about this is one of the things I think there's a lot of cool experiments on board. It's like one of those rovers, but it's the biggest rover we've made. I actually got to see the rover. Dane Sholin is this old student, now works for the Jet Propulsion Laboratory in Pasadena. He's a student from my classroom. And he's out there. So he gave me a tour and he got to see the rovers that they're using. These things are big now. Anyway, so on that rover, there's a helicopter. And so the helicopter is going to fly around Mars. It's going to fly around. It's going to take off, go do some surveying, come back, report back to us. So the problem with our rovers so far on Mars is they don't go very far. You know, even they may go miles and miles or kilometers. The first one only went about 10 feet, but it hit a rock. But the other ones have gone a long ways, but they're still limited. They're just rolling along, right? Now we can fly. And I think Brandon should probably answer this question. Why would it be an issue flying on Mars? Since Brandon's going into aerospace, right? Why is it an issue flying on Mars? Why not just in the same as flying on the Earth? What's the problem?
There isn't air, is there? I mean, I know there's an atmosphere, but
yeah, Mars has about 1% the atmosphere of the Earth.
yeah, it's like almost nothing.
Yeah, almost nothing. So you've got to have lift. If you're gonna fly a helicopter or a plane, you have to have lift. You have to have lower pressure on top of the blades and higher pressure below. But getting pressure itself, so that's going to be quite the feat. And they have it worked out. They have all kinds of mechanics there for it to fly. But it'll be interesting to see because it's hard. You cannot test that on Earth. You put it into a vacuum. They have the big vacuum chamber up in Cleveland, Ohio. They can run a lot of experiments in that vacuum chamber. And I guess they've done that. But that's going to be interesting. So anyway, to watch that landing, if you want to write about it, you can write about it, make a little report on it if you want, put it in your notebook, get points that way. So speaking of other planets, go ahead.
I don't know if you know this or not, but someone in this call, Mr. Anthony Yoon, was actually a finalist to name.
You are correct. I read that about you, Anthony. And that was to name what again?
It was
The
named the rover itself.
Okay. And what was your choice?
My choice was Fortitude.
Fortitude. I like that. Well, perseverance, fortitude. They kind of used your idea. That's cool. I like Fortitude. That would have been perfect. So did you get like runner up or something or?
I actually don't know. They never told me. But
Okay.
my essay is on a microchip that's on the rover.
Man, hey, can you include that and throw it on Facebook group?
Sure.
That's awesome. That's really cool. So yeah. Now, Anthony, are you looking to work for JPL or something one day?
I'm hoping to.
Okay. Well, Dane Sholin, he works for JPL and he was a student. He was on my robotics team. We'd won I think we were third in the world when he was there and second in the world for the years he was there. But he's really good. He's a super cool guy. He's a Renaissance man. He does everything. He's into all kinds of stuff. Him and I are always exchanging music and stuff. Really good taste, good sense of humor. Anyway, so he's out there in Pasadena and we can work out a tour if you can ever get out there to California. And I've had him, he gave a tour to Macy Boren, and Macy's now looking at aerospace. She's out at Long Beach State. She started off a music major and now she's aerospace. That may change next year, but anyway, so she got a tour of it. I can get you a tour with Dane, and if Dane knows you're from my class, you know he'll go all out for you. So and anybody else too, Brandon, whoever else. I mean, we need to put them all together. But thing is, you can't just say, "Hey, I'm going to take a tour on Tuesday." You have to have clearance through the U.S. government, and they'd run background checks on you and everything. So you can't. It's not that you can just walk in and get a tour. They're worried.
Yeah, JPL is like my dream job.
This is JPL at Pasadena. Beautiful area, campus. It's like a campus. And with Dane, he takes you to places that the tour doesn't go to. like back, like in the clean rooms and all that. You get the special access to projects he's working on. He's working on a robotic, he's working on a robot that climbs down the walls of, they think there's maybe tunnels in the moon. And so that we'd be living in the tunnels. There's like these canyons, I think. And so he's developing robots that have all these gadgets that come out of them automatically. They're autonomous robots, and they climb down walls and they come and they move along. So he showed me that project, and that's all, hush hush. Oops, oops. I'm not supposed to say anything. Well, oh well. No one's going to watch this but you guys. All right, so I'll probably get a knock on the door in the middle of the night. All right, so back to our Planet X. We got to get this thing done. Okay, so the gravity is we're saying is 25 centimeters per second, which isn't much. And now the last thing I want to do on this is, okay, so now let's plot what it would look like if we shot this ball out of a toy gun horizontally on the Earth. What would be the ball's path on Earth? Okay. Oh, by the way, we were supposed to find V final. Let's knock this out. Where are we at? Where are we at? Where are we at? Where are we at? Just lost everything. Okay, we're supposed to find V final, and the V final is really easy. We just use first blue. So V final, V not being 0, is just minus G tau. So whatever that is, you can plug that in for the planet. Now, so let's go back to this graph and let's quickly plot. Let me show you. Let me fess up to the mistake I made when I was blurry-eyed here during second hour. I said, oh, well, okay, let's go ahead and find out what it is on Earth. Well, I'm a low-hanging fruit guy, so I said, okay, let's do it this way. On Earth, let's just use the red equation, because it's always red equation, right? Delta x equals Vx times t. And that's the simplest way to go, so I always go the simplest way first. So delta x, then I'm going, okay, Vx is 60 centimeters per second. That's true. And then t is tau, which is 2.75. Oh, I wasn't thinking too well. 2.75 seconds, and I got 165 centimeters. Like, wait a minute. So what huge mistake. What was my flaw in my logic here? What flaw was that?
It doesn't account for acceleration.
Well, there is no acceleration in the X. And that's why I went to the X. I thought, well, I can get the answer really quick. But the 60 centimeters per second, that is true. That's the speed at which the bullet, little toy bullet, comes out of the gun. But what about this? That's only for Planet X. On Earth, it's not going to take that long to hit the ground on Earth. So I was using Planet X data. Planet X. I was using Planet X data. So we got to fix that. Oh, good grief. Okay, Planet X. So we got to find the Earth's time. And so let's find the time and then we can do it. So for Earth over here, how are we going to find time? Look at your blue equations. Which one should we use to find time? Obviously not the third. So but we don't know the final velocity, so it has to be the second. So on Earth, we have, in the y direction, we have delta y equals v naught y t minus 1/2 gt squared, but we catch a break there, that's 0. So don't worry about that. So the time on Earth then would be t equals the square root of -2 delta y over g, right? That's just solving for t. Okay, so we need that negative because the delta y is negative. So the time that it would take for the Earth would be -2 times -94, to keep it in CGS, centimeters divided by g, which is 981 now, centimeters per second squared. And so when you do that, what do we get for time? I don't remember. Small number. It took it 2.75 seconds on Planet X, but on Earth, 2 times 94 divided by 981 second square root, second answer 0.44. So we get only 0.44. So it took, so this is what you're used to, shooting a ball out of a cannon at that speed out of a little toy gun, it'll hit the ground, which isn't very tall. That's about a meter below you. It'll hit the ground about 3 feet below you in about half a second, less than half a second. Whereas on this planet, it took it almost 3 seconds. So like everything's slow motion, as far as falling on this planet. You throw a ball in the air, go have a sandwich, come back, and then you go catch it. It's that kind of thing. So but wait a minute, that didn't help us. There's no time on this graph. So what can I do with that 0.44 seconds now? Remember, I want to know how far out will this ball go? So the question is, now what? $137. Okay, I'll count time.
It's the VXT, right?
Yeah, let's just do the VXT now. Now with the correct time. So we say, okay, delta X is simply Vx, which is still 60 centimeters per second, times now 0.44 seconds. And we're seeing that it goes, it's going to go around 26 centimeters. So delta X is on the Earth, is a pretty pathetic little gun. The gun looks pretty badass on planet X, but you bring it to Earth and it goes poop. It lasts less than half a second, and it only goes 26 centimeters, about that far. So on Earth, it's 26 right here. Yeah. So on the Earth, this is the start, this is the end. I don't connect up with the straight line, of course. I got to make a really skinny parabola. So it's got to come off flat. My slope, this takes a little skill. My slope has to be flat up here because it comes off with no velocity. So without turning the thing off, let's go flat. And then it's got to end up, we can figure out we can figure out what the tangent line would be down here by finding the final velocity. I'm not going to do that. I'm just going to say, okay, it's steep. So it's something along these lines. Like that. So that's what the path would look like on Earth. Okay, so we have, now clean this up a little bit. Come on, now we're buffering. Okay, so we have, make this pretty. All right, so we have Earth's path, and we have it's here, and we have planet X path is there. Planet is being generous. Planet X path is here. Okay, so that's cool. And that's all that problem. So we're done with the front of that. Oh, you have extra credit here for you go-getters here. The future astrophysicists, solve that problem. It's worth 6 extra points. For class, I'm giving them two dynos. So that translates to 6 bonus for you guys. 6 bonus for that. And that involves, my hint is, it involves density, and it involves 4/3 pi r cubed, and it involves rho, which is density. So there's some things you got to think about for that one. And I'll eventually post a key to it. Now, the last thing I want to do before I turn you loose here is I want to look at, okay, the homework. So we were going to do number 1 today in class, but being a flex day and only some kids, I want people here tomorrow for this one. So save, don't work number 1. That's land air. That's a top 10 problem. Not hardest necessarily, but important problem that we'll do. It will be the hardest problem today until we get to the back. So we're going to work on 2 and 3. That's your cold homework assignment, meaning that you don't get a whole, not getting a whole lot of. I just want to see what happens. Then tomorrow we'll talk about them. But let me give you this heads up. Okay, now here's what I'm saying. I'm going to animate because I don't know if it's going to register with you in this few minutes that we have. But here we go. This is a type 2A projectile motion problem, okay, in all its glory. And it's just the purple path because it's a parabola, right? Okay. Well, I want you to see now. First off, when the object, football, baseball, whatever you're throwing, is launched from your hand or from a cannon or whatever it is, it's got an angle to it, right? It's not type 1 where it comes off horizontally. Now it's coming off at an angle. So there's a theta in there. Well, if there is, then there's going to be a upwards component to that velocity and a horizontal component to that velocity. And that's where now these problems become more complicated because now for type 2A and B, we bring in sines and cosines. So, even makes the simple red equation more complicated. Now, I asked this question in second hour. I said, this is called V naught X. Why is the not needed for the X? It is needed for the Y. But why is it kind of unnecessary to say V naught X? Who wants to answer that?
Would the V naught equal 0?
V naught Y equals 0. There is a V naught X. But why is it? There is a velocity in the X direction. But why call it? Why not just call it V naught and V final X? How does V naught X and V final X compare in projectile motion?
Is it the same?
Same. So there's no reason to say V naught X because it's just Vx. So a lot of times I won't even put the V naught on the X part of that. Okay, so that's the first thing when it comes off at that angle. So really, now the red equation just got a slight bit more complicated. Now it's V naught, and it is, okay. There is a V naught. I don't know what you get. There is a V naught, but that whole thing is just Vx. Because there is a V naught. V naught velocity does change in the Y direction, but it does not change in the X direction. So V naught cosine theta, because it's the adjacent side, stays constant the whole time. Okay. So I wanted to, before we get too into the working, just the minutia of working problems, to look at the big picture for a second. And this is why I think I need an animation here. I'm going to try and explain it to you. This purple type 2A projectile motion path is a combination of two things. It's a combination of the red equation, that's the conveyor belt part that etches out where that ball is along the horizontal, and the vertical part, and that's the Y. That's the part that's changing. Now we can drill down further than that, because really on the blue part, it's the second blue equation we're talking about. We're talking about it through time, right? We need time, we need delta Y, therefore it has to be the second blue. So in the second blue equation, the second blue equation is actually a combination of Newton's first law fighting the tax, the earth tax. Okay, so the Newton's first law of the second blue equation is this blue arrow. You see the vertical blue arrow? There's a couple of them there. Here's one. Once I finish this, we'll finish today. Once I finish the explanation. But this blue arrow here, okay, that has a length of V naught sine theta times t. And then that length keeps growing, right? And that's if we're on the planet that has no gravity, which doesn't exist. Social media may think it does, but there is no planet with no gravity. But if we were in a situation like interstellar space, there's no gravity, no dominant gravity, then the ball would, once it leaves your hand, if you're throwing a baseball, would just keep going on that same speed forever and ever and ever. But Earth whispers a little bit. It's very gentle. It's not as gentle as the moon, but It's pretty gentle, saying, you know, it's whispering to come back. And that initial whisper is this little guy, this little downward arrow here. You know, initially it's right, happens instantaneously, but once it starts to get big enough, see, but as time goes by, that grows, that little whisper starts to turn into a, hey, come back. It gets louder and louder. See, that arrow is getting bigger, but it's getting bigger exponentially. And so there's the formula for it, 1/2 GT squared. So it's a square of time. It's getting bigger. And that's the tax that you're paying. Well, eventually, if you throw a ball in the air, it'll start rising because, it shut me down again. I didn't know I didn't touch any that time. It starts rising. We'll keep talking until it shuts me down, and then bring it back. So it keeps rising, but the tax keeps being added exponentially until finally it hits the ground again. Now, this is Newton thinking this, and Newton said, you know, if I could get it going so that it fell at the same rate that the earth curved away from it, then it would never hit the ground. And so he invented orbits. That's how orbits. So Newton was the first one to say, he's saying about the moon and all, but to orbit the earth, he even came up with the speed it would take. If you can get the speed, and this is the thing you gotta know for aerospace, of course, if you can get the speed up to 17,500 miles an hour, you'll never hit the ground. As you fall, the earth falls away from you, curves away. As you fall, the earth curves away from you. And this is a famous Newton, not real experiment, but thought, it could call it Gedonks, the thought experiment. But as he's going to shoot a cannon from a high hill, and it'll keep falling to the earth keeps falling away. And eventually that cannonball will come around, hit you in the butt. And he said, at that point, we've orbited the earth. So here he is in 1700, predicting orbit satellites orbiting the earth. All right, and they still use Newton's numbers today. It's pretty good when 300 years later, they're still using your data, your information. Okay, so now I got, all I got left is for you to do the 2 cold assignments, 2 and 3. A little bit of help there, but you can look at the tape. I think 2 is on there on the comments somewhere. So check that out, and then we'll see how we did tomorrow. Okay, stop the sharing. Anybody got a question? I'm really over considering it's Wednesday. So any questions before we stop the recording?